Hello, my name is Andreia and I'm going to present to you the paper Eurocode Structural Fire Design of Brazilian Masonry Buildings. The authors are Andreia Romero Fanton, Camila de Queiroz Moreira, and Rangel Costa Lage, from Structural Modeling and Monitoring Laboratory, University of Campinas, Brazil, and the professors Carla Neves Costa, Luiz de Almeida, and Leandro Mouta Trautwein, from University of Campinas, Brazil. So this is our team of students, me, Andreia Fanton, Camila Moreira, and Rangel Lage. So, the topics of these presentations are Introduction, Measuring in Fire Situations, Brazilian Recommendations, Eurocode Recommendations, ACI Recommendations, Australian Recommendations, the measuring room temperature, and the case study. So in Brazil, we have an increase in the demand for housing constructions, and there are several construction techniques here to do this. The structural masonry is a more economical, modern, and rational construction practice. But we need to know the behavior of masonry structures in case of fire, the structural and material scale, and the large number of descriptive parameters. In Brazil, there is no specific Brazilian standard for structural fire design of masonry structures. The Building Fire Safety Regulation of the State of São Paulo instructs the use of Eurocodes in the absence of a specific national standard for structural fire design. The Brazilian Study Committee is drafting the base text for a next standard to cover this gap regarding the fire behavior of structural masonry. This paper is going to develop a case study for dimensioning a Brazilian structural masonry building, comparing the results for clay and concrete units in fire situation according to procedures in Eurocode 6 Part 1-2. A literature review was done in order to understand the difference between recommendations from Brazil, Europe, United States of America, and Australia. So let's understand the behavior of masonry in fire situation. Fire separating elements, such as masonry walls, only one side of each element is exposed to high temperatures. The differential thermal expansion produces thermal bowing, and the layers of protections of these materials are prevention, detection, evacuation, compartmentation, suppression, and structural resilience. But not all layers must be presented in a building, but all must be considered at least. Here, we've made a summary of all those international codes that presents something about designing masonry structures in fire. First of all, we are going to understand how are the Brazilian recommendations. The vertical ceiling system needs to follow minimum fire requirements. Brazil recommendations related to structural fire design are quite new. The most important ones are fire design of concrete structures, fire resistance requirements for building construction elements, fire design of steel and composite structures, structural construction components determination of the fire resistance, and fire test wall and dividing wall without structural functions, fire resistance, method of test. Now we are going to see the recommendations from Eurocode. The basic requirements formulated for masonry structures in case of fire include load-bearing capacity, the R function, integrity, E function, and the thermal insulation, the I function. The following types of walls may react significantly different to fire. So here we have a summary of fire models and structural models related. From fire models we can have nominal curves and parametric curves, and also gas temperature non-uniform in a compartment, which forms a multi-zone models and real fire. And from a structural model, we can do a member analysis, a subframes analysis, and a global analysis. So if we combine parametric curves and member analysis, we see that in the future it will be possible to do tests and tabulated data. But now we can do simplified calculation method and advanced calculation method. And now the ACI recommendations. In ACI, the equivalent thickness of masonry wall is the sum between the equivalent thickness of the block and the equivalent thickness of its finish. And the Australian Code presents two options to design masonry walls subjected to fire. The first one is a tabular method, respecting the tabulated thickness limits, wall slimness, and reinforcement cover. And the second one is the method based on laboratory tests, using design abacuses provided by block manufacturers. So let's get started with measuring room temperature situation. So how does this thing work in Brazil? In the past, in Brazil, we had two different standards to analyze structural masonry. The one related to concrete units and the other one related to clay units. But now we have a new standard which has both unit types, concrete and clay. So now let's understand the building description for this case study. In this case study, the design rules in Eurocode 199612 were applied to a 3-story commercial building considered built in structural masonry. The building has 2 rooms per floor and 2.9 meters ceilings. Here we can see the floor plan and the schematic section of the building. As a common practice in Brazil, all the walls were taken as structural masonry. The wall thicknesses chosen in the preliminary design process were 160 millimeters, 140 millimeters from the blocks, and 10 millimeters of cement and sand applied on the faces. The Eurocode has several tables divided according to the compressive strength of the blocks, the density of the blocks, and the related design load in the fire situation combination and the design resistance load. The material of the wall block can be clay, dense aggregate concrete, and lightweight aggregate concrete. The studied wall in this case study is wall 3 from our design. It is a single-leaf wall separating load-bearing external wall. The first analysis is going to be developed using concrete masonry, dense and lightweight aggregate concrete units. Considering dense and lightweight aggregate concrete units, table NB32 of the Eurocode must be used. In Brazil, dense aggregate is commonly used, so it was considered in this case study. Because of this, the block strength in the net area is between 6 to 35 MPa, and there's a finish with a minimum thickness of 1 centimeter on both sides. For the wall studied, wall 3, criteria array must be met. And we have 2 different functions: load-bearing function, avoiding premature collapse of the structure, and separating function, limiting fire spread beyond designated areas. Concrete unit masonry in this case study has vertical rolls with void volumes between 25% and 60%, as we can see in this table here from Eurocode. The compressive strength of the unit was taken as 10 MPa. And here we see that in the design we need to find Fk, and we need a constant from table 3.3, and the compressive strength of the mortar, Fm, so the Fk is 5.54. The design vertical load resistance, NRD, is an equation multiplying the capacity reduction factor, the design compressive strength of the masonry, and the loaded horizontal cross-sectional area of the wall. In this case study, we have all this information here, height of 2.9 meters. So, we find an NRD of 301.96 kilonewtons per meter. So here, with the table NB32, we can find the minimum wall thickness for fire resistance classification, remembering that we are in Ray criteria, and here we have the results in minutes. So, in a Brazilian standard, we find that for this wall, we need a 60-minute TRRF. In Eurocode, we find a time between 30 and 180 minutes. So our conclusion is that for a 60-minute TRRF, the building must have a minimum thicknesses of 100 to 140 millimeters. And now for clay masonry, clay units, we are going to follow the table NB12 from Eurocode 1996 part 12, and all the other parameters are the same. So here we are going to compare. We also have group 2. The compressive strength is taken as 6 MPa, so the FK is going to be changed. We can compare here. For concrete we had 5.54, now we have 3.42. The design vertical load resistance calculated the same way. In this case study, we have the same parameters here. So we are going to find an NRD of 181.5 kilonewtons per meter. In concrete units, using concrete units, we had 301.96. And it's bigger here than the clay units. The fire resistance, now we are going to calculate the same way, and here also it is smaller than 0.6. And we have here to find the minimum wall thickness for 90 minutes. For this, we have here a minimum thickness of 100 to 140. So here the same way, we have in Brazil a standard which recommends a 60-minute TRRF. In Eurocode for clay units, we found a 90 minutes. So the conclusion is that for a 60-minute TRRF, the building must have a minimum thickness of 90 to 100 millimeters. If we go back here, we find that for 60 minutes, we need a wall thickness of 90 to 100. The final result, so here we are going to compare some parameters. FB for concrete and clay, they are different. So the NRD are also different, and the ray in time is truly different here. So the final conclusion is we need human life safety, and we need to prevent property damage. So these are the main goals of fire safety. In Brazil, there's a lack when talking about fire structural design code related to structural masonry. So the final conclusion, in this study, both unit types, concrete and clay, were inside the Eurocode requirements when comparing the Brazilian TRRF obtained from our standard. The unit mechanical properties weren't considered as a Brazilian block with different aggregates. It's necessary to develop research in this area approaching the basic parameters of structural fire behavior of Brazilian masonry. Comparing unit types concrete and clay, it can also be concluded that the concrete unit reached a bigger design vertical load resistance NRD as expected. On the other hand, the clay units obtained a closer result for ray, 90 minutes, comparing to the Brazilian code requirement. For a 60-minute TRRF, a Brazilian requirement, the building must have a minimum thickness, Eurocode requirement, of 100 to 140 millimeters in case of using concrete units, and 90 to 100 millimeters for clay units. These are our references. Use it in this paper. So thank you very much for the attention. My name is Andreia Romero Fanton. I am a PhD student in University of Campinas, Brazil, and this is my email of contact. And I would also like to thank Unicamp, LabMen, CAPES, CNPq, FUNCamp for all the support. Thank you very much.